The cosmos holds secrets far stranger than fiction. In a distant corner of space, one galaxy stands out as a spectacular oddity, the Tadpole Galaxy. Its bizarre, twisted shape is the result of a violent cosmic collision, and within its long tail and warped core lurk some of the universe's most peculiar objects. By the end of this journey, you will have explored 50 of its most baffling inhabitants, from runaway stars to phantom black holes. What cosmic force could warp an entire galaxy into such a strange form, and what kind of objects are born from such chaos? What do you think is the most mysterious thing a galaxy can hide? That bizarre, stretched-out tail is only half of the story. The true heart of the mystery lies in the tadpole's distorted core. This central region is not the calm, orderly spiral you might expect. Instead, it resembles a cosmic whirlpool caught in a violent spin. The gravitational pull from a smaller galaxy that punched straight through it has left the core permanently twisted and off balance. This immense force has churned the very fabric of the galactic center into a state of beautiful chaos. Within this turbulent environment, vast clouds of gas and dust are constantly colliding and compressing. This triggers frantic, explosive bursts of star formation, lighting up the core with the brilliant glow of millions of newborn stars. But such a disrupted environment cannot settle down. It fosters instability, creating a landscape where stars are born only to be flung into wild orbits or torn apart by gravitational tides. The greatest secret this warped core might be hiding, however, is a supermassive black hole with truly unusual properties. Most large galaxies anchor a supermassive black hole at their center, but the one within the tadpole is different. The galactic collision may have thrown it off its axis, or perhaps even pushed a second black hole into a dizzying dance with it. This could create a binary system, two monstrous gravitational engines circling each other in the galactic heart, their immense forces warping space-time itself in unpredictable ways. How do you hide a supermassive black hole? You surround it with the brilliant, chaotic light of a galactic wreck, a perfect camouflage for the universe's most enigmatic objects. Stretching across an astonishing 280,000 light-years, this cosmic streamer is a river of potential. It is composed of colossal clouds of hydrogen gas and fine cosmic dust, all ripped from the galaxy's main body during that ancient collision. This was not a gentle tug, but a gravitational tsunami that pulled entire stellar nurseries out into the void, leaving a luminous scar across the heavens. Within this river, the conditions are unlike anything in a normal galactic disk. The gas is not evenly spread, but clumped into dense, turbulent knots. As these massive clouds of material crash into one another within the tail, they trigger violent, localized bursts of new star formation. Imagine a string of cosmic firecrackers, each one a brilliant blue cluster of young stars, igniting one after another along the entire length of this celestial ribbon. These are not the stable, long-lived stars like our Sun, but massive, hot, and short-lived giants that burn intensely blue before ending their lives in spectacular supernova. Their very existence is a paradox, born in the isolated darkness of intergalactic space from the debris of a galactic wreck. What does it mean for a star to be born so far from any galactic center, in a place that was never meant to cradle new suns? Deep within the tadpole's chaotic tail, a new object blazes with the light of a violent death. Astronomers call it the sparkler, a supernova remnant glowing with an intensity that defies simple explanation. It is the brilliant, expanding ghost of a star that no longer exists, a cosmic echo of a single, catastrophic moment. The light we see now is the aftermath, the stellar material flung outward at millions of kilometers per hour, heating the surrounding gas to incandescent fury. But the sparkler is more than just a beautiful corpse. Its light carries a unique chemical fingerprint, a signature written in the language of atomic spectra that reveals an astonishing truth. This remnant is astonishingly rich in heavy elements like gold, platinum, and uranium. These are not forged in the quiet life of a star, but in the unimaginable violence of its final seconds. Such a specific chemical cocktail points to a very particular kind of stellar death. The star that became the sparkler was likely a supernova of type 1a, a thermonuclear bomb so perfectly calibrated it briefly outshone its entire host galaxy. This occurs in a binary star system where a dense white dwarf siphons material from its companion until it reaches a critical mass and detonates completely. The sparkler's light is therefore a message in a bottle cast across space and time. It tells us not just about one star's end, but about the very building blocks of the Tadpole Galaxy. The presence of these heavy elements scattered by the explosion will one day seed future generations of stars and planets. What other cosmic riches are being forged in the darkness of this galactic tale waiting to be discovered? This river of cosmic debris has just given birth to something spectacular. Drifting in the isolation of the tidal tail is a brilliant grouping of stars known as the Blue Blob Cluster. Its members are not the steady yellow light of mature suns, but the searing blue-white radiance of stellar infants. These are massive, volatile stars, each one burning its nuclear fuel at a ferocious rate. Their intense blue color is a direct result of their extreme heat and youth, a telltale sign of a stellar nursery that ignited only a few million years ago. To find such a vibrant young cluster here, so far from the galaxy's main disk, is like discovering a bustling nursery in the middle of a deserted highway. It defies the old rules of star formation. Normally, stars are born in the dense, calm spiral arms of a galaxy, where gas clouds can slowly collapse under their own gravity. The Blue Blob Cluster tells a very different story, one of chaos and violence as a creative force. Its birth was not slow and steady, but rapid and brutal. The same colossal gravitational forces that stretched the Tadpole Galaxy also compressed these isolated pockets of gas. Think of it like squeezing a handful of snow into a hard, compact ball. When those giant gas clouds in the tail were violently squeezed during the collision, they reached a critical density and ignited into stars almost instantly. This has triggered star formation on an epic scale, a direct and dramatic consequence of the galactic wreck. The cluster is a living fossil, a perfect snapshot of the precise moment that cosmic violence translated into celestial creation. What does the sheer brilliance of these blue stars tell us about the future of this orphaned cluster? They are destined to live fast and die young, exploding as supernova that will, in turn, seed the tail with new elements and trigger yet another wave of creation in this endless cycle. But the brilliant bursts of starlight and the glowing remnants of supernova are not the only forces shaping this galaxy. Holding the entire chaotic structure together is something far more mysterious, an entity we cannot see at all. Astronomers call it the invisible giant, a truly colossal halo of dark matter that envelops the Tadpole Galaxy. This unseen substance does not emit, absorb, or reflect any light, making it completely invisible to our telescopes. Yet its presence is felt everywhere. It is the cosmic glue that prevents the galaxy from flying apart, especially after the violent collision that stretched it into its current form. Without the immense gravitational pull of this dark matter halo, the stars and gas in that long, flowing tail would simply drift away into the emptiness of intergalactic space, dissolving the tadpole's unique shape entirely. So how do we detect something we cannot see? We watch how it influences the things we can see. By meticulously mapping the speeds and orbits of stars and hydrogen gas clouds throughout the galaxy, scientists can measure the total gravitational force acting upon them. The result is startling. The visible matter, all the stars and glowing gas we can observe, accounts for only a tiny fraction of the gravity required to hold the tadpole together. The rest, the overwhelming majority of the galaxy's mass, must be this invisible dark matter. It is like watching leaves swirling in a windstorm. You cannot see the wind itself, but you can see its powerful effect on everything it touches. What makes the tadpole's invisible giant even stranger is its shape. In a typical, undisturbed galaxy, the dark matter halo is a relatively smooth spherical cloud. The tadpole's halo, however, is believed to be profoundly lopsided, stretched and distorted by the same ancient collision that warped the galaxy's stars. This uneven distribution of dark matter is like a hidden, asymmetrical anchor, its gravity pulling more strongly on one side than the other, which helps explain why the galaxy's tail streams out in one particular direction and why the core remains so unsettled. This invisible architecture dictates the visible form, a silent giant whose ghostly hands molded the tadpole we see today. What other invisible forces are at work in the cosmos, sculpting the universe in plain sight? Streaking through the void at the edge of the tadpole's tail is a true cosmic fugitive. Astronomers have spotted a star moving so fast it is not merely orbiting the galaxy, it is actively escaping its gravitational pull forever. This hypervelocity star, nicknamed the Runaway, is traveling at millions of kilometers per hour, a speed so immense it will eventually leave the galaxy behind entirely, destined for the cold, empty vastness of intergalactic space. How does a single star achieve such an incredible velocity? The most compelling theory points to a violent encounter in the galaxy's chaotic core. Imagine the supermassive black hole, or perhaps the binary pair of them, lurking at the tadpole's heart. If a binary star system ventured too close to this gravitational monster, a complex dance of forces could have occurred. One star would be captured by the black hole's immense gravity, swinging into a tight orbit. The other star, acting as a gravitational slingshot, would be flung outward at a tremendous fraction of the speed of light, ejected from the galaxy like a stone from a catapult. The Runaway is that stone, a solitary traveler whose very existence is a direct relic of a close call with the ultimate cosmic predator. Its trajectory is a frozen moment, a permanent record of that ancient, violent interaction. Another possibility is that it was once part of a tight binary system where its companion star exploded as a supernova. The sudden, asymmetric detonation could have blown the star away, rupturing the gravitational bond that held them together and sending it careening across the galaxy. The Runaway's composition, a chemical fingerprint read from its light, might one day reveal which of these dramatic origin stories is true. It carries the secrets of the galaxy's most violent environments stamped into its very atmosphere. What other celestial projectiles have been launched from the tadpole's turbulent center, and where will their endless journeys ultimately lead? One of the most puzzling objects in the tadpole's tail is a feature defined by what is not there. Astronomers have mapped a colossal, ghostly cloud of neutral hydrogen gas, a structure so vast it could contain the building blocks for millions of stars. Yet when they point their most powerful optical telescopes at its location, they see only an empty void, a perfect darkness. This cloud is a cosmic ghost, a reservoir of pure potential that has stubbornly refused to ignite. It drifts in the tidal stream as a silent, dark enigma. The mystery of its existence hinges on a fundamental question of cosmic evolution. Why has this immense collection of gas failed to collapse under its own gravity and birth new suns? The answer may lie in its ancient origins. One compelling theory suggests this cloud is not a product of the galactic collision, but something far older. It could be a pocket of primordial material, a relic from the early universe that has remained virtually untouched for billions of years. In this scenario, the cloud is too pristine. It lacks the heavy elements and the cosmic dust grains that act as seeds for star formation. Without these tiny particles to help the gas clump together and cool down efficiently, the cloud remains in a stable, diffuse state, a sleeping giant that has never been awakened. Another possibility is that this ghostly cloud is all that remains of a tiny, ancient dwarf galaxy that was torn apart by the tadpole's gravity during the collision. The gravitational tides would have ripped the galaxy apart, scattering its stars into a faint, undetectable stream while leaving this larger, more diffuse cloud of gas behind. The violence of the event may have stirred the gas just enough to prevent it from settling into the dense, cold knots necessary for star birth. It is a galactic fossil, the shimmering ghost of a galaxy that was utterly consumed. This leaves us with a profound thought. The universe is filled not only with the brilliant objects we can see, but with the silent, dark potential of what has not yet happened and what may never be. What other invisible structures are drifting between the stars, holding secrets from a time before the first galaxies even formed? Nestled within the tadpole's long tail is a structure of stunning symmetry, a nearly perfect circle of intense blue light known as the Ring of Fire. This brilliant halo is not a single object but a necklace of superheated star-forming regions, each one a colossal stellar nursery burning with the fierce energy of millions of newborn suns. Its geometric perfection seems utterly out of place in the chaotic debris stream, a cosmic mystery written in fire. How could such a flawless ring form in the aftermath of such violence? One compelling explanation points to a phenomenon called a density wave. Imagine tossing a stone into a calm pond and watching the perfect circular ripples expand outward. A density wave is a gravitational analog of that ripple. It is not a physical movement of material, but a wave of compressed gravity that travels through the galactic disk. As this wave passes through, it squeezes the diffuse gas and dust clouds, causing them to rapidly collapse and ignite into stars. The Ring of Fire could be the frozen imprint of such a wave, a single ripple that briefly brought order to the chaos, triggering star formation in a perfect circle before the wave continued on its journey. Yet there is another, more dramatic possibility. The ring might be the direct result of a second, smaller impact. Long after the main collision that created the tadpole's tail, a tiny dwarf galaxy or a massive dark matter clump could have punched straight through the gas-rich debris. Just like that stone in the pond, the gravitational shock of this impact would have sent powerful ripples propagating through the gas. The leading edge of the strongest ripple would have compressed the gas into a dense, circular shell that then fragmented into the brilliant string of star clusters we see today. This would make the Ring of Fire a bullseye, marking the precise point of a later, unseen cosmic strike. Whether born from an internal rhythm or an external hammer blow, this Ring of Fire is a testament to the universe's strange tendency to create perfect order from the deepest chaos. What other perfect shapes are hidden within the tangled webs of colliding galaxies, waiting for a keen eye to discover them? The brilliant chaos of the tadpole's core may hide its most violent secret yet. Astronomers have gathered compelling evidence that not one, but two supermassive black holes are locked in a tight, gravitational dance at the galaxy's very heart. This cosmic duet is the direct relic of the ancient merger that forged the tadpole's strange shape. When that smaller galaxy plunged through the larger one, its own central black hole was carried along for the ride. Instead of a swift collision, the two monstrous objects became trapped in a mutual orbit, circling one another in a relationship that has lasted for millions of years. We cannot see them directly, but their presence is betrayed by the frantic motion of stars around the galactic center. These stars whip around at impossible speeds, following erratic paths that can only be explained by the immense, combined gravitational pull of two incredibly massive objects, not one. The energy of their orbital dance is so colossal it must be radiating outward in a form we are only just learning to detect: gravitational waves. These are not waves of light or sound, but literal ripples in the fabric of space-time itself. Think of the universe as a still pond, and these two black holes as incredibly heavy weights spinning rapidly on its surface. Their motion sends out faint, rhythmic pulses that travel at the speed of light, subtly stretching and squeezing everything in their path, including the space we occupy. While these waves from the tadpole are too faint for our current instruments to detect directly, Their theoretical existence tells us that this binary system is slowly but steadily losing orbital energy. With every rotation, the two black holes spiral a tiny bit closer together. This cosmic waltz cannot last forever. In billions of years, their orbits will decay completely, leading to a final, cataclysmic merger that will shake the very foundations of the galaxy, releasing more energy in a single burst than all the stars in the universe combined. What other cosmic tremors are echoing across the universe, born from the violent embraces of invisible giants? Far from the chaotic core, another object defies all expectations of stellar death. Drifting through the tadpole's outskirts is a structure of such precise geometry it appears almost artificial, the Red Rectangle Nebula. This is not the gentle, round glow of a typical planetary nebula, but a stark, bipolar shape with sharp, box-like corners and vivid rung-like bars, resembling a celestial ladder viewed from the side. It surrounds an aging central star, a sun-like body in its final throes, desperately shedding its outer layers into space. The mystery is not its death, but the bizarre form of its funeral shroud. How can the violent, chaotic process of a star's death produce such clean, angular lines? The secret lies in a hidden dance at the nebula's heart. The dying star is not alone. It is locked in a tight orbit with a companion star, a stellar duo whose gravitational interplay acts like a cosmic sculptor. As the primary star puffs out its outer layers, this gas and dust does not expand evenly in all directions. Instead, the powerful gravitational field of the secondary star funnels the ejected material into two opposing cones, like two ice cream cones placed tip to tip. From our vantage point, looking directly at the side of this double cone, the edges appear to form a sharp, rectangular shape. The stunning rungs across the rectangle are even more telling. They are thought to be periodic outbursts from the central star, a series of pulsing ejections that create concentric waves of dense gas and dust. As these expanding shells of material run into the walls of the conical funnels, they create the illusion of solid bars, painting a series of steps onto this cosmic ladder. The intense red color comes from a specific type of carbon-based molecule, illuminating the entire structure. This precise celestial architecture proves that even in death, a star's final form can be dictated by an unseen partner, a gravitational choreography that turns a stellar demise into a geometric masterpiece. What other dying stars are hiding their true, beautifully complex shapes simply because we are viewing them from the wrong angle? Shining with a cold, steady light deep within the tadpole's tail is a collection of cosmic diamonds. The diamond dust cluster is not made of newborn stars, but of stellar ghosts, the exposed cores of long-dead suns known as white dwarfs. These are not the brilliant blue giants of the cluster we saw earlier, but the faint, dense embers of stars that have exhausted their nuclear fuel and faded away. Normally, such ancient objects should be cooling down, radiating their leftover heat into the void over billions of years. Yet these particular white dwarfs are puzzlingly hot and bright, shining with an unexpected intensity. They are behaving like embers that have been suddenly stoked, glowing far more fiercely than their great age would suggest. This reignition points to a violent and recent chapter in their long lives. The most likely explanation is that these dead stars are not alone. Each one is likely locked in a tight gravitational embrace with a companion star. As the two stars orbit one another, the immense gravity of the white dwarf can strip material, primarily hydrogen, from its partner. This stolen gas does not simply fall onto the dead star's surface. It accumulates in a searingly hot, dense layer. When the pressure and temperature at the base of this layer reach a critical point, a runaway thermonuclear explosion ignites. The entire surface of the white dwarf detonates in a colossal flash, causing it to brighten by thousands of times in a matter of hours. This is not a supernova that destroys the star, but a surface explosion called a nova. The star we see shining so brightly in the diamond dust cluster may be one that has recently undergone such an eruption, its surface still seething from the blast. Or it could be in a state of constant, simmering fusion, steadily burning the material it steals from its companion. This makes the cluster a celestial graveyard that is strangely, violently alive. Each of these diamond-like cores is a potential time bomb, repeatedly erupting as it feeds on its neighbor. What does this cycle of stellar death and reignition tell us about the final, turbulent stages of a star's life? A strange deception lies within the tadpole's tail. One particular object, catalogued as a faint smudge of light, was initially thought to be a simple star cluster within the tidal stream. But its light told a different story, revealing it to be an entire galaxy far in the distant background, an interloper whose image has been hijacked by the tadpole's immense gravity. This cosmic trick is one of the universe's most fascinating phenomena, gravitational lensing. The combined mass of the tadpole star's gas and its enormous halo of dark matter creates a profound warp in the fabric of space-time. Think of it as a vast, cosmic magnifying glass embedded within the galaxy itself. When the light from this distant background galaxy travels toward us, it must pass through this warped region. The distorted space does not provide a straight path. Instead, it bends the light rays, stretching and amplifying the image of the galaxy behind it. This lensing effect does not just magnify the interloper, it often twists its shape into bizarre arcs and multiple mirrored images. The tadpole acts as a natural telescope, allowing us to see a galaxy that would otherwise be far too faint and small to observe in any detail. This accidental alignment provides a unique window into the early universe, letting us study the formation of stars in a galaxy billions of light years further away than the tadpole itself. The presence of this lensed interloper also serves as a direct probe, confirming the staggering total mass of the Tadpole Galaxy. The degree of distortion in the background galaxy's light allows astronomers to precisely weigh the entire system, dark matter and all. What appears as a simple smudge is therefore a double revelation, a ghostly image from the cosmic deep that simultaneously illuminates the hidden structure of the foreground. How many other distant galaxies are being similarly magnified and twisted by the universe's massive lenses, their true forms waiting to be decoded from the light? Hidden within one of the tadpole's stellar nurseries is a cosmic lighthouse broadcasting on an invisible frequency. This is the methanol maser, a natural laser that beams out intense microwave radiation instead of visible light. The word maser itself stands for microwave amplification by stimulated emission of radiation. It is a process where molecules, energized by the fierce radiation from newborn stars, release that energy in a coordinated, amplified beam. Think of it like a laser, but operating in the microwave part of the electromagnetic spectrum, a precise, powerful signal cutting through the cosmic static. The specific molecule at work here is methanol, a simple alcohol, and its unique signature is a powerful clue to the environment around it. For a methanol maser to fire, conditions have to be just right. It requires dense, swirling clouds of gas and dust that are being violently agitated by the intense heat and stellar winds from massive, young stars still embedded in their birth cocoons. The presence of this specific methanol maser tells astronomers they are looking at a region of extremely active, ongoing star formation, a place where the chaotic forces of creation are still in full swing. The beam acts as a natural probe, illuminating the structure and dynamics of these otherwise obscured stellar nurseries. By studying its precise frequency and strength, scientists can map the invisible motions of these gas clouds, measuring their speeds and densities with incredible accuracy. It is a whisper from the heart of the storm, a signal that reveals the hidden turmoil where new solar systems are being forged. What other invisible beacons are flickering throughout the galaxy, each one a coded message about the violent and beautiful processes of cosmic birth? Deep within the tadpole's spiral arm, a silent heart beats in the language of pure energy. This is the X-ray binary, a pair of stars locked in a lethal gravitational embrace. One star is a normal, sun-like body, while its companion is something far more exotic and dense, a neutron star or a stellar mass black hole. Their cosmic dance is a one-sided affair. The immense gravity of the dense object relentlessly strips material, primarily hydrogen, from its larger partner. This stolen gas does not fall directly onto the surface. Instead, it forms a searingly hot, spinning disk of doomed matter, an accretion disk that spirals inward at nearly the speed of light. As the material in this disk is compressed and heated to millions of degrees, it does not shine in visible light but erupts in powerful, flashing X-rays. The rhythm of these emissions is what astronomers call its heartbeat, a regular, pulsating signal that cuts through the cosmic background. This heartbeat is a direct probe into the most extreme environments in the universe. The precise timing of the pulses reveals the orbital period of the two stars, while the energy of the X-rays tells us about the temperature and density of the accretion disk itself. For a system with a neutron star, the pulsations can be incredibly regular, timed to the dizzying spin of the city-sized stellar corpse. Each flash is a lighthouse beam from the edge of a gravitational abyss, a signal that allows us to study the behavior of matter under forces so intense they defy all earthly comparison. This binary system is a natural laboratory, demonstrating in real time how gravity can tear a star apart and use its very substance to light up the void. What other violent rhythms are pulsing in the darkness, each one a testament to the destructive and creative power of cosmic relationships? A stark silhouette of absolute blackness drifts against the starry backdrop of the tadpole's tail. This is the dark globule, a cosmic inkblot so dense and cold it swallows the light from every star behind it. It appears not as a glowing cloud, but as a perfect hole punched through the galaxy, a void defined by its profound absence of light. Within its shadowy depths, temperatures plummet to just a few degrees above absolute zero, and the gas and dust are packed together with incredible density. This globule is a stellar nursery in deep hibernation, a cocoon of potential holding the raw materials for an entire solar system. The mystery is not its existence, but its profound stability. With so much material crammed into such a small space, gravity should have taken over long ago, causing the cloud to collapse inward and spark a new star. So why does this pocket of pure potential remain frozen in time? The answer seems to lie in a delicate balance of forces. While gravity is constantly pulling inward, two powerful factors are pushing back. The first is internal gas pressure. The random, jostling motions of the molecules within the cloud generate a subtle outward force, like billions of microscopic springs resisting the crush of gravity. The second, and perhaps more crucial force, is the faint but persistent pressure of starlight from the surrounding galaxy. The intense radiation from nearby brilliant blue stars and supernova remnants acts like a cosmic wind, gently buffeting the outer layers of the globule and helping to support it against a full collapse. This dark globule has found a precarious equilibrium, a state of paused animation where these opposing forces have reached a temporary standoff. It is a celestial seed waiting for the right trigger to awaken. A nearby supernova shockwave or a collision with another cloud could be the final nudge that tips the balance, overwhelming the supporting forces and allowing gravity to finally win. When that happens, this patch of darkness will blaze with the light of a newborn star, transforming a cosmic void into a brilliant beacon. What other dormant seeds are scattered throughout the galaxy, their futures hanging on a thread of perfect, silent balance? The dark potential of the tadpole's ghostly gas clouds is mirrored by a more tangible and equally ancient act of consumption. Wrapped around the galaxy like faint, shimmering ribbons are the stellar streams of a cannibalized dwarf galaxy. These are not clouds of gas, but the scattered remains of billions of stars, their orbital paths stretched into long, looping arcs that trace the final moments of their home. This is galactic archaeology in action, a direct view of how large galaxies grow over cosmic time by devouring their smaller neighbors. The process is a slow, gravitational unraveling. As the dwarf galaxy was pulled into the tadpole's immense gravitational field, immense tidal forces began to tug it apart. The stars on the side closer to the tadpole felt a stronger pull than those on the far side, and this difference over millions of years stretched the entire dwarf galaxy into a river of stars. These streams now orbit the tadpole like cosmic spaghetti, gradually mixing into its halo, their individual identities fading forever. Within one of these streams, astronomers have pinpointed a dense knot of stars, a disrupted globular cluster that once orbited the dwarf galaxy's core. This cluster is a ghostly anchor, a surviving piece of the dwarf's heart that resisted immediate dissolution. Its stars are chemically distinct, older, and with a different mix of heavy elements than the tadpole's native populations. Studying this cluster is like finding a unique pottery shard at an ancient archaeological site. It tells a specific story about the original culture, the dwarf galaxy, before it was absorbed. This act of cannibalism is not a rare event. It is the standard mechanism of galactic growth. Our own Milky Way is currently digesting several dwarf galaxies in the same way, their stellar streams silently weaving through our galactic halo. The tadpole simply offers a more dramatic, frozen snapshot of this eternal cosmic process, a reminder that the majestic galaxies we see today are built from the remains of countless smaller ones. What other faint streams of stars are winding their way through the darkness, the final echoes of galaxies that no longer exist? Its rhythmic pulse is written in light, a slow, cosmic heartbeat that takes nearly a full Earth year to complete. This is the Mira variable star, a swollen red giant in the tadpole's tail that swells and shrinks with a profound, predictable regularity. For 330 days it brightens, expanding to an immense size and shining with a deep orange-red glow. Then, for the next 330 days, it slowly fades and contracts, its light dimming to a faint ember before the cycle begins anew. This is not the frantic flicker of a star in its death throes, but the stable, resonant breathing of a sun in its final, stable phase of life. The entire star is pulsating, its outer layers rhythmically rising and falling like a colossal lung. The driving force is a delicate and powerful balancing act deep within its core. As the star fuses helium into carbon, immense energy builds up beneath its opaque outer layers. This trapped radiation causes the star to expand dramatically. But as it expands, it cools and the outer layers become more transparent, allowing the pent-up energy to finally escape. With this release, the pressure drops and gravity pulls the star's outer atmosphere back inward, starting the cycle all over again. This Mira variable is a celestial metronome, its steady rhythm a direct window into the complex internal mechanics of an aging star. But its true significance for astronomers lies not just in its pulse, but in its unexpected address. Finding such a perfectly timed variable star out here in the isolated tidal tail is a profound clue. Stars like this are typically very old, having spent billions of years evolving in the calm, crowded disk of a galaxy before reaching this pulsating stage. Its presence so far from the main galactic body suggests a remarkable history. This star was likely born in the tadpole's original disk long before the collision ever happened. When the smaller galaxy tore through, the gravitational chaos did not destroy the star, but instead plucked it from its ancient orbit and flung it into the newly forming tail. It is a cosmic refugee, an elderly citizen carrying the chemical signature of the pre-collision galaxy within its atmosphere, now performing its final, magnificent dance in the darkness of intergalactic space. By studying its pulsations and its composition, we are reading the autobiography of a star that witnessed the galactic wreck firsthand. What other ancient storytellers are drifting in the tail? their steady rhythms encoding secrets from a time before the tadpole had its strange, stretched-out shape. A different kind of force sculpts the chaos in another part of the galaxy, a silent power detected not by light but by the twist of radio waves. This region, known as the magnetic monster, possesses a magnetic field of staggering strength and complexity, its lines of force tangled into knots by the galaxy's violent past. We observe its presence through polarized radio emissions, a telltale signature where the radio waves are not just streaming out randomly, but are aligned, vibrating in a specific direction as they travel through this tortured magnetic landscape. This is the ghostly fingerprint of a field under immense stress. The leading theory for its origin takes us back to the moment of collision. When the two galaxies merged, their individual magnetic fields did not simply cancel each other out. Instead, they were stretched, sheared, and woven together by the colossal turbulence, much like two handfuls of spaghetti being violently stirred in a pot. The motion of the superheated gas swirling at incredible speeds acted like a dynamo, amplifying these tangled fields to extraordinary intensities. This monstrous magnetic field is not a passive observer, it is an active player in the tadpole's evolution. It can channel the flow of high-energy particles, guide the collapse of giant gas clouds, and even influence the very direction in which new stars are born. It is an invisible architecture of force, a relic of ancient violence that continues to shape the galaxy's destiny. What other unseen forces, born from cosmic collisions, are silently guiding the birth and death of stars across the universe? Radiating from the tadpole's depths is a cloud of light so immense it defies simple scale. This is the Lyman alpha blob, a colossal, amorphous glow of hydrogen gas stretching for hundreds of thousands of light years. It does not shine with the familiar white light of stars, but with a very specific, pure color in the ultraviolet part of the spectrum, a signature known as the Lyman alpha line. This single, brilliant tone is the fingerprint of hydrogen, the universe's most basic element, being excited by a powerful but hidden energy source. The sheer size of this object is its primary mystery. It is not a compact star cluster or defined nebula, but a vast, diffuse halo of energized gas, a cosmic fogbank shining with its own internal, ethereal light. So what could possibly illuminate such an enormous volume of space? One compelling theory points to a frenzy of creation happening within the cloud itself. The tadpole's violent history may have triggered the most intense starburst event imaginable, birthing millions of scorching, young stars all at once. These massive stars flood their surroundings with ultraviolet radiation, which then energizes the surrounding hydrogen fog, causing the entire cloud to fluoresce in that specific Lyman alpha hue. It would be like a city so vast and bright that its collective glow illuminates the entire foggy county it sits within. Yet there is another, more dramatic possibility. The true engine behind the blob's glow might be a hidden monster, an active galactic nucleus powered by the supermassive black hole at the tadpole's core. As vast quantities of matter spiral into the black hole, the accretion disk becomes so unimaginably hot that it erupts with a flood of high-energy radiation. This torrent of energy then streams out into the galaxy, lighting up the hydrogen gas like a cosmic ultraviolet lamp. The Lyman alpha blob, therefore, is either the sign of the most prolific stellar nursery in the region, or it is the brilliant shadow cast by a voracious black hole, its invisible power made visible across a structure of breathtaking scale. This object challenges our very definitions, blurring the line between a cloud of gas and a single, coherent entity. What other colossal structures are hiding in plain sight, their true nature revealed only by the unique color of their light? A faint, luminous scar curves gracefully against the dark canvas of space, an arc of pure light that seems to defy the natural order. This is the gravitational lens arc, a celestial mirage created by the tadpole's immense gravity warping the very path of light itself. The arc is not a physical structure within the tadpole, but the stretched and magnified image of a galaxy billions of light years behind it. The combined mass of the tadpole star's gas and its colossal dark matter halo acts as a natural cosmic telescope, bending the fabric of space-time around it. When the light from that incredibly distant background galaxy travels toward us, its path is distorted as it passes through this warped region. Instead of traveling in a straight line, the light is bent around the tadpole, creating this brilliant, curved apparition. It is a perfect demonstration of Einstein's theory of general relativity in action, where mass tells space how to curve and curved space tells light how to move. This natural telescope provides an invaluable gift to astronomers. The galaxy whose light forms the arc is so far away it would normally be an invisible, unreachable speck. But the lensing effect amplifies its light, making it bright enough for our telescopes to study in detail. We can see the structure of its spiral arms, map its regions of star formation, and even estimate its distance, all thanks to this cosmic magnifying glass embedded within the tadpole. The arc is therefore a double revelation. It is a beautiful, ghostly image from the edge of the observable universe, and it is also a precise scientific instrument. The specific shape and brightness of the arc allows scientists to measure the total mass of the Tadpole Galaxy, including the invisible dark matter that makes up most of its weight. This single curved line of light is both a window into the deep cosmos and a scale for weighing a galaxy. What other impossibly distant objects are being brought into view by the universe's own gravitational lenses, revealing worlds we were never meant to see? Deep within the tadpole's spiral arm, a single point of light outshines all others, but its brilliance is completely invisible to our eyes. This is an ultra-luminous X-ray source, a cosmic powerhouse beaming out more X-ray energy than a million suns. It appears as a tiny, star-like pinpoint, yet its energy output defies any simple explanation. A typical stellar mass black hole, formed from a collapsed star, simply cannot reach such staggering levels of brightness. There is a fundamental limit, known as the Eddington limit, which dictates how bright an object can be before its own radiation pressure pushes material away and shuts off its fuel supply. This object blows past that limit with ease, so what cosmic engine could possibly be at work here? One leading theory points to a true astronomical oddity, an intermediate mass black hole. This would be a missing link in the black hole family, heavier than the stellar mass remnants of dead stars, but lighter than the supermassive giants that anchor galaxies. It would possess the perfect gravitational pull to gorge on matter at a ferocious rate, generating the colossal X-ray flux we observe. Another possibility is just as strange. Perhaps it is a common stellar black hole, but one that is feeding in an unusual way. Instead of a smooth, orderly disk of infalling material, it might be accreting matter in a thick, puffy disk that traps its own radiation. This allows the black hole to binge on gas far beyond its normal limit, like a fire burning in a sealed room, growing hotter and more intense than should be possible. A third, even more exotic idea involves beaming. The intense X-rays might not be radiating out in all directions equally, but could be focused into narrow, powerful jets like a cosmic lighthouse. If one of those beams happens to be pointed directly at us, the source would appear far brighter than it truly is from other angles. This tiny, brilliant point is therefore a profound mystery, challenging our basic understanding of how black holes grow and feed. It could be a middleweight champion proving its existence, or a small predator with a uniquely gluttonous appetite. What other invisible beacons are hiding in plain sight, their true nature masked by the sheer intensity of their own light? Another celestial butterfly graces the darkness of the Tadpole Galaxy, a fleeting vision of beauty born from stellar death. This is the Butterfly Nebula, a pre-planetary nebula caught in a spectacularly brief phase of transformation. It is not the final state of a star, but a single, magnificent moment suspended between life and death, lasting only a few thousand years. At its heart beats a dying sun, a star that has exhausted its nuclear fuel and is now shedding its outer atmosphere into the void. But this ejection is not a gentle, uniform puff of smoke. It is a focused, high-speed jet of gas and dust streaming from the star's poles, flying outward in two perfectly opposite directions. From our vantage point, this creates the stunning illusion of two vast, luminous wings, a cosmic Rorschach test painted across space. The secret to this perfect symmetry lies in a hidden dancer. The central star is likely locked in a tight gravitational embrace with a companion, a smaller stellar partner whose influence is profound. As the dying star expels its outer layers, the companion's gravity acts like a sculptor's tool, funneling the erupting material into two narrow, opposing jets. It is the universe's version of placing a thumb over a garden hose, transforming a chaotic spray into a directed, powerful stream. The intense radiation from the exposed, hot core of the star then illuminates these twin outflows, causing them to glow with an ethereal light. We are witnessing a star's final breath being shaped into a work of art by an unseen partner. This butterfly will not last long. The central star will soon heat up even more, its ultraviolet radiation boiling away the surrounding gas and transforming the nebula into a fully fledged planetary nebula. For now, it remains a perfect, symmetrical snapshot of a stellar metamorphosis, a reminder that even in death, the universe strives for balance and breathtaking form. What other fleeting moments of cosmic beauty are unfolding across the galaxy, their entire glorious lives over in the blink of a cosmic eye? A sudden, sharp crackle of radio energy breaks the cosmic silence, a flash of impossible power compressed into a few thousandths of a second. This is a fast radio burst, and within the Tadpole Galaxy, one source has done something extraordinary. It has repeated. Most of these cosmic flashes are one-off events, a single, brilliant shout in the dark that never happens again. But the repeater in the tadpole sends its powerful signal again and again, a sporadic, unpredictable pulse that defies easy explanation. The energy released in each brief burst is staggering, equivalent to the sun's total output over several days, all focused into a blink of an eye. So what kind of object can store up that much energy and release it so violently and so repeatedly? The suspects are as strange as the signal itself. One compelling candidate is a highly magnetized neutron star, a magnetar. These city-sized corpses of dead stars possess magnetic fields so intense they can literally twist the star's solid crust. Imagine a neutron star undergoing a starquake, a sudden, catastrophic shift in its crystalline surface. This event could release a titanic wave of energy, shaking the star's magnetic field and producing a firestorm of radio waves that we detect as a single, sharp burst. The repeating nature suggests this magnetar is particularly active, its crust constantly cracking under the strain of its own unimaginable magnetic forces. Another, more exotic possibility involves a neutron star in a tight orbit with a massive, bloated companion. As the neutron star plows through the stellar wind of its partner, immense amounts of material could crash onto its surface in violent, episodic avalanches. Each impact would trigger a thermonuclear explosion on the neutron star's surface, a detonation so powerful it generates the observed radio flash. This would make the repeater a cosmic clock, its bursts timed to the chaotic rhythm of its orbital dance. The very existence of this repeater offers a tantalizing opportunity. Because the bursts travel through the tadpole's own gas and magnetic fields, they act as a probe. Each frequency of the radio wave is slowed by a slightly different amount as it passes through this diffuse material, a delay that allows astronomers to measure the total amount of matter the signal has encountered. This gives us a new way to weigh the invisible stuff between the tadpole stars, using these brilliant, fleeting flashes to map the galaxy's hidden depths. This repeating signal is more than just a mystery. It is a tool, a chance to listen in on one of the universe's most volatile and energetic conversations. What other coded messages are hidden within these random bursts, waiting for the right moment to be understood? This cluster of ancient suns holds a chemical secret, a purity that modern stars have lost. Nestled within the tadpole's halo is a globular cluster composed of millions of stars, all of them astonishingly deficient in metals. In the language of astronomy, a metal is any element heavier than hydrogen or helium, the building blocks forged in the Big Bang. This cluster is metal poor to an extreme degree, meaning it contains only trace amounts of carbon, oxygen, iron, and all the other elements that make up our world and our bodies. Its stars are cosmic fossils, pristine relics from a time before the universe was seeded with the ashes of dead generations. They are the universe's first immigrants, a cluster that did not originally form with the tadpole, but was captured by its gravity during the chaotic merger, an entire family of ancient suns adopted into the chaotic new galaxy. Their profound lack of heavy elements tells a clear story. These stars were born from a cloud of primordial gas that had never been enriched by supernova explosions. They ignited in the universe's infancy from material that had only existed for a few 100 million years. When we look at this cluster, we are seeing a living snapshot of the second generation of stars ever to shine. The first generation, called Population 3 stars, were hypothetical giants made of pure hydrogen and helium that lived fast, died young, and in their supernova deaths polluted the cosmos with the first metals. The stars in this metal-poor cluster formed from that lightly polluted material. They are the direct descendants of those first cosmic pioneers. Studying their light is like reading a history book written in the simplest atomic alphabet, revealing the conditions of a younger, more violent cosmos. Their longevity is a testament to their modest beginnings, as lower masses allowed them to burn their fuel slowly for billions of years, outliving countless brighter, richer stars. How many other primordial clusters like this are drifting through the halos of galaxies, each one a silent time capsule from the dawn of time? A deep chill permeates the very fabric of space here, a cold so absolute it registers not as light but as a profound shadow. This is the infrared dark cloud, a stellar nursery so young and dense that its own potential smothers all visible glow. We see it only in silhouette, a sprawling ink blot against the warm, infrared background light of the tadpole's distant stars. Within this frigid murk, temperatures hover just a dozen degrees above absolute zero, and colossal tendrils of gas and dust drift in near-perfect stillness. This is the quiet before the storm of creation, a place where gravity is only just beginning its patient, relentless work. The cloud is a cosmic womb in its earliest possible stage, a reservoir of raw material where future suns are mere whispers of coalescing matter. How does a star begin its life? It starts here in these dark, silent nurseries, vast, diffuse pockets of hydrogen and helium, seeded with fine grains of silicate and carbon dust, slowly begin to draw together. The process is imperceptibly slow, a gentle tug of gravity that over thousands of years gathers these microscopic particles into larger clumps. These clumps, in turn, attract more gas and dust, growing steadily denser and more massive. They are not yet protostars, but dense cores, the very embryos of solar systems. Their growth is a fragile balance, the cloud's own internal turbulence and the faint pressure of starlight from outside work to keep it supported, much like the dark globule we encountered earlier. But here, the scales are beginning to tip. In the darkest, densest heart of this cloud, a few particular cores have reached a critical threshold. Their gravity is now strong enough to overcome all outward pressure, and they have begun their final, unstoppable collapse. It is a fall that will last 100,000 years, a silent, invisible plummet that will end in the first flicker of nuclear fusion and the birth of a new star. We are witnessing the universe in a state of pure potential, a frozen moment where the ingredients for entire worlds are gathered. waiting for the single, decisive spark to set them ablaze. What other shadows in the Tadpole Galaxy are not voids but cradles, holding the latent light of suns that have not yet learned to shine? Far out in the tidal stream, a knot of stars and gas has achieved a startling degree of self-reliance. This is no simple cluster, but a tidal dwarf galaxy candidate, a massive, swirling structure within the tail that possesses its own distinct gravity and is actively forming new stars. It challenges our very definition of what makes a galaxy, blurring the line between a temporary structure and a permanent cosmic citizen. This candidate did not form in the primordial early universe like most galaxies. Instead, it is a direct offspring of the tadpole's violent collision, assembled from the galactic debris cast out during that ancient encounter. The immense gravitational forces of the merger did more than just tear material away. They also compressed vast clouds of gas into this dense, coherent pocket. Over time, this isolated knot gathered more material from the surrounding tail, growing massive enough for its own gravity to dominate its local environment. It began to spin and form its own spiral structure, nurturing stellar nurseries from its internal gas reserves. It is a cosmic phoenix rising not from ashes but from the wreckage of a galactic disaster. The central question is profound. Is this a true, independent galaxy? For it to be considered one, it must be held together primarily by its own visible mass, without needing the dark matter halo of its parent galaxy. This is the crucial test. Most galaxies are anchored by vast, invisible halos of dark matter, but a tidal dwarf galaxy might be different. It could be a purely baryonic entity, built solely from the stars and gas ripped from the tadpole's disk. If so, it would be a unique class of object, a galaxy born without a dark matter skeleton. Its existence a direct challenge to our models of cosmic structure. Watching this object is like witnessing the live birth of a new island in a cosmic archipelago. Will it remain bound by its own gravity for billions of years, evolving on its own solitary path? Or will the subtle, persistent pull of the Tadpole Galaxy eventually draw it back, reabsorbing its rebellious child in a future act of cosmic cannibalism? This candidate holds the answer to whether chaos can create lasting order, and if new galaxies are still being sculpted in the violent wakes of the old. Its steady pulse has faltered, the cosmic metronome falling out of rhythm. Among the tadpole's vast stellar population, one Cepheids variable star refuses to follow the rules that astronomers have relied on for a century. These stars are the universe's standard candles, celestial lighthouses whose predictable pulsations allow us to measure intergalactic distances with incredible precision. The relationship is beautifully simple. The longer the pulsation period, the more intrinsically bright the star is. By comparing its known intrinsic brightness to its apparent dimness from Earth, we can calculate its distance with remarkable accuracy. But this particular Cepheids is anomalous, its pulse erratic and its brightness fluctuating in a way that defies the established models. It is like a clock that sometimes ticks steadily, then suddenly speeds up or slows down for no apparent reason, throwing off every calculation based on its rhythm. This single misbehaving star creates a ripple of uncertainty through our maps of the Tadpole Galaxy. If we cannot trust its pulse, how can we be sure of its true distance or the scale of the structures around it? The source of its irregularity points to a deeply complex stellar interior. A typical Cepheids pulsation is driven by a layer of ionized helium deep within the star, a zone that rhythmically traps and releases radiation, causing the entire star to expand and contract. This anomalous Cepheids, however, might have a different internal chemical composition, or its pulsations could be interacting with a deeper, secondary layer of instability, creating a chaotic interference pattern. Another possibility is that the star is not alone. It could be part of a binary system where the gravitational tug of an unseen companion subtly distorts its pulsations, pulling the stellar heartbeat in and out of sync. The violent environment of the tadpole itself may be the ultimate culprit. This star might be a recent immigrant flung into its current location from a different part of the galaxy during the collision, a process that could have fundamentally altered its structure or spin. Its erratic behavior is a stark reminder that even our most trusted cosmic tools are individual objects with their own unique histories and complexities. What other fundamental rules of the cosmos are being quietly bent or broken by the strange inhabitants of this distorted galaxy? A subtle, invisible fire burns across the entire Tadpole Galaxy. This is the gamma-ray glow, a faint but pervasive light of the highest energy radiation, bathing every star and cloud in a silent atomic storm. It is not a single point of light, but a diffuse, all-encompassing energy field, the ghostly signature of the galaxy's violent nature. Gamma rays are the universe's most potent photons, born from its most extreme processes, and here they form a uniform fog, a testament to the relentless particle acceleration happening everywhere at once. The source of this glow lies in a relentless hailstorm of cosmic rays, subatomic particles like protons and electrons that have been accelerated to nearly the speed of light. These cosmic bullets, likely launched by supernova explosions and the turbulent magnetic fields we encountered earlier, fly chaotically throughout the galaxy. The glow itself appears when these high-speed particles slam into the nuclei of slow-moving hydrogen atoms drifting in interstellar space. Each collision is a microscopic, violent event, a shattering impact that creates new particles and releases a flash of gamma-ray light. It is the same physics as a particle accelerator like the Large Hadron Collider, but playing out on a galactic scale with natural forces far more powerful than anything we could ever build. The puzzle for astronomers is not the process but the sheer intensity. The tadpole's gamma-ray glow is unexpectedly bright. The galaxy's violent history has essentially turned it into a perfect cosmic ray factory. The constant churn of stellar births and deaths, the shock waves from countless supernovae, and the twisted magnetic fields all work together to keep the cosmic ray population unnaturally high. There are more high-speed particles flying around and more interstellar gas for them to collide with than in a common galaxy. This makes the entire tadpole a single glowing system, an object defined not by what we see with our eyes, but by the invisible high-energy fury that permeates its every corner. What does this persistent atomic fire tell us about the true, energetic cost of a galactic collision? A price paid not in light, but in the relentless, invisible rain of radiation that shapes its future. Wrapped around the tadpole like the layers of a cosmic onion are vast, faint shells of stars, each one a ghostly ripple frozen in time. This immense shell structure is not a product of the galaxy's current state, but a direct echo of its violent origin. When that smaller galaxy plunged through the heart of the tadpole, it did not just stretch out a tail, it sent powerful gravitational shock waves reverberating through the entire system. Think of dropping a heavy stone into a still pond. The impact creates a series of expanding rings. In a galaxy, these rings are not made of water, but of stars, gently tugged into new orbits by the passing gravitational disturbance. Each shell represents a specific moment in the merger, a snapshot of how far the shockwave had traveled at a particular time. The stars within these shells are not new, they are ancient citizens of the original galaxy that were gravitationally kicked into these vast, arching paths. They now drift slowly outward, creating these faint, concentric halos that can span hundreds of thousands of light years. Mapping these shells is an act of galactic archaeology. By measuring their distances, their speeds, and their spacing, astronomers can effectively rewind the cosmic clock. The number of shells tells them how many major close encounters occurred during the merger. The spacing between them reveals the relative speeds and masses of the two colliding galaxies. A tight cluster of shells suggests a slow, drawn-out gravitational dance, while widely spaced shells point to a faster, more violent impact. This structure is therefore a living timeline, a permanent record of a catastrophic event written in the language of stellar orbits. It allows us to look at the serene-looking tadpole today and read the precise chapters of the violent collision that shaped it, seeing not just the final twisted form, but the individual waves of force that created it. What other ancient echoes are written into the structure of seemingly calm galaxies, their turbulent histories hidden in plain sight? Deep within another stellar nursery, a different kind of cosmic whisper echoes on a specific, invisible frequency. This is the water maser, a natural amplifier that uses water molecules instead of methanol to broadcast its powerful signal. The process is similar, but the molecule involved makes all the difference. When water molecules in a dense cloud of gas are energized by an intense source of radiation, they release that energy in a coordinated, amplified beam of microwave light. It is a laser made of steam, a precise signal born from the most common compound in the universe. The presence of a powerful water maser is a telltale sign of an environment undergoing violent change. These masers often flare up in two very different yet equally dramatic locations. The first is in the swirling disks of gas and dust that surround newborn massive stars. As these stellar infants ignite, their fierce radiation and powerful stellar winds slam into the surrounding material, creating shock waves that energize the water molecules and power the maser emission. The second, and even more powerful, location is in the tumultuous accretion disk feeding a supermassive black hole at the galaxy's core. Here, the intensities are almost unimaginable, with gas swirling at a significant fraction of the speed of light and temperatures soaring to millions of degrees. In this cosmic maelstrom, water molecules are jostled and excited to an extreme degree, producing a maser signal of staggering power. By mapping the precise locations and velocities of these water masers, astronomers can achieve something remarkable. They can chart the structure and spin of a black hole's accretion disk with incredible precision, measuring features light years across from an impossible distance. This natural amplifier turns a cloud of hot steam into a cosmic ruler, allowing us to trace the invisible architecture of the most violent engines in the universe. What other simple molecules are acting as invisible beacons, their faint signals illuminating the dynamics of cosmic monsters? Perhaps the most staggering idea to emerge from the tadpole's chaos is a missing monster. The controversial hypothesis suggests that one of the two supermassive black holes thought to be waltzing at the galaxy's core is no longer there. During the violent gravitational interplay of the merger, the three-body dance between the two black holes and the incoming galaxy's core may have become unstable. The physics is akin to a cosmic slingshot, where one of the black holes was flung away at tremendous speed, ejected from the galactic center entirely. This would leave behind a single, bewildered black hole and create a true runaway, a billion solar mass behemoth now drifting silently through the darkness of intergalactic space. We cannot see it directly, of course, but astronomers search for its ghostly signature, the trail of destruction it would leave in its wake. As this invisible giant plows through the diffuse gas and dust clouds of the tadpole's halo, its immense gravity would act like a celestial snowplow, compressing the material in front of it. This violent compression would trigger frantic, episodic bursts of new star formation directly along its path. The result would be a linear string of brilliant blue star clusters, a dotted line of cosmic fireflies tracing the otherwise invisible journey of the fugitive black hole. Finding such a trail would be like discovering the footprints of a mythical beast, a path of creation pointing directly back to a moment of unimaginable violence. The very idea challenges our understanding of how galaxies evolve, suggesting that the most massive objects in the universe can be forcibly evicted from their homes, becoming dark, solitary wanderers in the void. How many other supermassive black holes are now drifting between galaxies, completely invisible, their presence betrayed only by the unexpected cradles of light they leave behind? A single crimson jewel burns with a deep, smoky light in the tadpole's spiral arm. This is the carbon star, a swollen red giant whose very atmosphere has been transformed into a cosmic forge for soot. Its deep red color is not just a sign of its cool surface temperature, but a direct result of its unique chemical makeup. Within its churning outer layers, a remarkable imbalance has occurred. Through processes deep in its core and dredged up to the surface, carbon atoms now outnumber oxygen atoms. This simple shift in chemistry changes everything. The carbon readily links together into complex molecules and tiny particles of dust, creating a smog so thick it dims the star's light to a rich ruby glow. This star is quite literally painting itself red with its own waste. The carbon dust does not stay put. The star's immense size gives it only a weak gravitational grip on its outer layers, and its powerful light exerts a constant radiation pressure. This combination gently but persistently pushes the newly formed dust grains outward, creating a slow cosmic wind that carries the carbon away into the surrounding void. Think of a dandelion releasing its seeds on a gentle breeze, but on a scale encompassing entire solar systems. This ongoing expulsion is a form of celestial recycling with profound consequences. The carbon and other heavy elements being shed by this star will eventually mix with the surrounding interstellar gas and dust. Millions or billions of years from now, that enriched material will collapse to form new stars, new planets, and perhaps even the chemical precursors to life. The diamonds we cherish and the complex organic molecules that form our bodies were all forged in the hearts of stars like this one, and then scattered across the galaxy by their gentle, dusty winds. This cool, red giant is not just a dying star, it is a silent farmer sowing the seeds of future complexity across the cosmos. What other fundamental ingredients for worlds and life are being patiently manufactured in the atmospheres of unassuming stars like this? Wrapped around the tadpole's main disk like a celestial hula hoop, a ghostly ring of stars and gas spins on a completely different plane. This polar ring structure orbits at a right angle to the galaxy's primary disk, a rare configuration that suggests the tadpole's chaotic history involved a very specific kind of cosmic theft. While the main collision stretched the galaxy into its tadpole shape, this ring is likely the lingering evidence of a separate, quieter event. Imagine a smaller, gas-rich galaxy venturing too close and being captured, not by a direct impact, but by being slowly torn apart over billions of years. Its stars and gas were not absorbed into the main disk, but were instead strung out into this vast perpendicular orbit, tracing a path around the galaxy's poles like a belt around a waist. The existence of such a structure is a delicate clue. It tells astronomers that the material was captured from a trajectory almost perpendicular to the tadpole's original disk. This specific angle of approach allowed the stolen matter to settle into this stable, yet seemingly precarious orbit, held in place by the combined gravitational pull of the main disk and the invisible dark matter halo. Without that precise alignment, the debris would have simply mixed into the main body of the galaxy, leaving no distinct ring behind. This faint, spinning halo is therefore a fossilized record of a specific orbital encounter, a cosmic snapshot of a long-vanished galaxy's final path. What other subtle structures are hiding in plain sight, their unique geometries telling silent stories of ancient captures and mergers? Beyond the familiar spiral arms and the brilliant chaos of its core, the Tadpole Galaxy hides a secret halo of creation. Its influence stretches far into the seeming emptiness, marked by a faint, pervasive glow only visible in the ultraviolet part of the spectrum. This is the extended ultraviolet disk, a vast, ghostly region where new stars are being born in the galactic hinterlands, far from the crowded stellar nurseries of the main disk. We see this not with our own eyes, but through the sharp gaze of space telescopes designed to see this high-energy light. The presence of this ultraviolet glow is the unmistakable signature of hot, young, massive stars. These are stellar giants that live fast and die young, burning their nuclear fuel at a ferocious rate and flooding their surroundings with intense ultraviolet radiation. Their existence here in these sparse outer realms is a profound puzzle. How can stars form in such isolation where the clouds of gas and dust are supposed to be too thin and too diffuse to collapse? The answer seems to lie in the galaxy's violent past. The same colossal gravitational shockwaves that stretched the tadpole's tail and warped its core did not simply stop at the visible edge. Those ripples of force traveled outward, propagating through the galaxy's outermost halo of gas. Like a stone dropped in a pond sending ripples to the very edge, these gravitational waves compressed the tenuous gas in the galactic suburbs, nudging just enough material over the critical threshold to trigger star formation. It is a subtle, delayed reaction to an ancient cataclysm, a final whisper of the collision that is still sparking new suns billions of years later. This extended disk forces us to redefine the true boundaries of a galaxy. The tadpole is not just the bright, visible structure we see in optical images. It is a much larger entity whose processes of birth and evolution continue in a faint, ultraviolet corona, a realm of stellar genesis happening in the quietest, darkest reaches of space. What other galactic giants are hiding similar halos of youthful light, their full scale only revealed by the invisible fire of their youngest and most volatile stars? The brilliant chaos of the tadpole's core hides its engine behind a cosmic veil. Buried deep within the galactic center lies a supermassive black hole in a state of ferocious activity, an obscured active galactic nucleus whose true power is smothered by its own fuel. This is not a simple void, but a ravenous engine completely shrouded in a thick, donut-shaped torus of cosmic dust and gas. From our viewpoint, this dense structure sits like a colossal smoke ring around the black hole, blocking its direct light from our optical telescopes. We cannot see the brilliant accretion disk or the powerful jets that might be erupting from its poles, because the torus absorbs that visible and ultraviolet light, re-radiating it as heat. This hidden monster reveals itself only when we look with the right eyes in the specific wavelengths of infrared and X-rays. In infrared, we see the warm glow of the dusty torus itself, heated by the intense radiation from within. In X-rays, we can detect the most energetic photons which punch through the obscuring material like a searchlight through fog. This obscuration solves a long-standing puzzle about the tadpole. The galaxy shows all the signs of having a powerfully active core with swirling gases and energetic processes, yet it lacks the brilliant quasar-like glare we see in other active galaxies. The thick torus provides the answer, orienting itself in such a way that its dusty rim blocks our direct line of sight to the central engine. We are essentially viewing the galactic nucleus from the side, peering at its brilliance through a cosmic keyhole. This configuration turns the entire core into a natural laboratory for studying how black holes feed. The torus is not just a static screen, it is the very reservoir of fuel. Vast amounts of gas and dust from the surrounding galaxy are funneled inward, piling up in this swirling structure before making its final, doomed plunge into the black hole's event horizon. The obscuring torus is therefore both the veil and the dinner plate, simultaneously hiding the monster and providing its meal. What other cosmic giants are hidden in plain sight, their true ferocity muted by the very material that sustains them? A colossal void drifts within the tadpole's spiral arm, a cosmic cavity so vast it could swallow entire solar systems. This is the superbubble, a gigantic sphere of emptiness carved from the galaxy's interstellar medium. Its sheer scale is the result of a coordinated stellar assault, a sustained campaign of violence from a family of massive star clusters at its heart. These clusters are home to the galaxy's most volatile stellar giants, stars that burn through their fuel in mere millions of years. During their short lives, they unleash torrents of charged particles, stellar winds that scream outward at millions of kilometers per hour. This relentless gale scours the surrounding space, pushing the ambient gas and dust ahead of it like a cosmic plow. But the true sculpting force is even more dramatic. The most massive of these stars do not fade quietly. They explode as supernova one after another. Each detonation delivers a hammer blow to the cavity's inner wall, a shockwave of unimaginable power that injects more energy and pushes the bubble's boundary ever outward. The superbubble is not a static hole, it is a dynamic, expanding entity. Its surface is a roiling shock front, a spherical wave of compressed gas and energy that races through the galaxy. As this wall of force plows into the surrounding interstellar medium, it rams into slower-moving clouds of hydrogen. The collision is violent, compressing the gas to incredible densities and triggering the collapse of new, unintended stellar nurseries right on the bubble's periphery. This creates a beautiful paradox where the forces of stellar death and destruction inadvertently create the perfect conditions for new stars to be born. We are witnessing a self-perpetuating cycle of creation and destruction on a galactic scale. The bubble's expansion also tells a deeper story about the tadpole's energy budget. By measuring its size and rate of growth, astronomers can calculate the total energy injected by its stellar engines, a number that often defies belief, equivalent to thousands of supernovae. This single structure is a testament to the collective power of massive stars, proving that when they work in concert, they can reshape the very architecture of their galactic neighborhood. What other immense voids are silently growing within nearby galaxies, their quiet expansion hiding a history of furious stellar violence? The tadpole's chaotic heart beats in a rhythm we cannot hear, but its vibrations ripple across the cosmos. Every tight orbit of its binary black holes and every frantic dance of its dense star clusters sends a tiny shiver through the very fabric of space-time. These individual tremors are far too faint to detect on their own from such a vast distance. Yet the combined effect of millions of these events across the universe creates a constant, low hum known as the gravitational wave background, an ocean of space-time ripples in which the tadpole is a distinct, if subtle, voice. Think of it like a vast, crowded stadium. You cannot make out the words of any single person, but the collective roar of the crowd forms a powerful, pervasive sound that fills the entire arena. The Tadpole Galaxy, with its particularly violent and crowded core, contributes its own unique frequency to this cosmic noise. Each time a pair of neutron stars spiral into a final embrace, or a star is flung at high speed from a dense cluster, a tiny pulse of gravitational energy is released into the universe. The binary black hole system at the galaxy's center is its most powerful instrument in this orchestra. With every rotation, as those two monstrous objects spiral imperceptibly closer, they pump energy out into the void in the form of these waves. Over millions of years, the cumulative effect of all this microscopic stretching and squeezing from countless galaxies like the tadpole builds up into a stochastic background, a random sea of whispers that underlies all of reality. Detecting this background hum is one of the greatest challenges in modern astronomy, requiring observatories that measure the subtle distortions in space itself over years of observation. The tadpole, in its beautiful distortion, acts as a natural laboratory, showing us how the universe's most chaotic events write their history not in light, but in the silent, rhythmic warping of the cosmos. What other secrets about the universe's structure are encoded in this faint background static, waiting for us to learn how to listen? A solitary sun drifts in the profound darkness between galaxies, a cosmic castaway from the tadpole. This is the intergalactic star, a stellar orphan flung so violently from its home that it now wanders the void, untethered from any galactic anchor. Its journey began millions of years ago in the galaxy's chaotic core, where gravitational forces are extreme enough to play stellar pinball. The most likely scenario involves a close encounter with the binary supermassive black holes. A star system that ventured too near would have been caught in a ferocious gravitational slingshot, with one star captured and the other ejected at a staggering fraction of the speed of light. This star is that projectile, a runaway that achieved escape velocity and is now condemned to an eternity of solitude. Another possibility is that it was a member of a tight binary system where its partner exploded as a supernova. The sudden, asymmetric blast could have shattered their bond, kicking the star out of the galaxy like a stone from a shattered window. Its light, when analyzed, tells a poignant story. The chemical composition of this star is a fossil record, revealing it was born in the tadpole's disk, rich with the heavy elements forged in previous stellar generations. It is not a primitive star from the early universe, but a modern sun, complete with the ingredients for planets suddenly and irrevocably exiled. Imagine the view from a hypothetical world orbiting this star. The night sky would be almost perfectly black, the tapestry of the Tadpole Galaxy receding into a mere smudge of light, growing fainter with every passing millennium. There would be no nearby stellar nurseries, no close neighbors to light up the heavens, just the cold, constant glow of distant galactic islands. This star's destiny is to grow old and die in utter isolation, its eventual death as a white dwarf or supernova witnessed by no one. How many other such lonely suns are adrift in the immense gaps between the galaxies, their light too faint for us to see, each one a silent testament to the violence that can exist at the heart of cosmic beauty. A newborn star announces its violent arrival with a blade of pure energy. Deep within one of the Tadpole's stellar nurseries, a narrow, high-speed jet of material screams outward from the poles of a young protostar, a celestial geyser of cosmic proportions. This is not the gentle glow of a stable sun, but the focused, frantic scream of a star fighting to be born. The protostar at the heart of this maelstrom is still gathering mass, a swirling ball of gas and dust still collapsing under its own immense gravity. As this material falls inward, it does not plunge directly onto the star's surface. Instead, it forms a furious, spinning disk, a whirlpool of doomed matter. The physics of this chaos are channeled, with some of the infalling gas and magnetic energy being focused and blasted away from the star's poles at nearly the speed of light. These jets are the star's way of clearing its throat, a necessary release of angular momentum that allows the rest of the material to continue spiraling inward and finally ignite the fires of nuclear fusion. The true spectacle, however, happens where this scalding blade of particles smashes into the surrounding nebula. The jet rams into the slower moving clouds of cold hydrogen gas, creating violent shockwaves that heat the gas to incandescence. The collision point glows with an ethereal, knotted light, a Herbig-Haro object that marks the terminal end of this stellar blowtorch. These glowing knots are not static, they move, and by comparing observations taken years apart, astronomers can actually track the jet's motion as it plows through the interstellar medium, clearing out a cavity and illuminating its own path of destruction. It is a breathtaking demonstration of how the most violent acts of creation can paint the cosmos with fleeting, beautiful light. How many of these cosmic blowtorches are currently carving their way through the Tadpole's dark nurseries, their brilliant tips marking the exact location where a new solar system is struggling to be born. Even the dust here tells a strange story. Scattered between the Tadpole stars, invisible to the naked eye, are countless trillions of microscopic dust grains. To astronomers, this dust is more than just cosmic dirt, it is a chemical fingerprint. By analyzing the specific wavelengths of light these grains absorb and scatter, a technique called spectroscopy, scientists can determine their exact composition. What they found was deeply puzzling. The dust in the Tadpole Galaxy is not like our own, it is alien. The spectroscopic data reveals signatures of minerals and crystal structures that are rare or entirely absent in the interstellar dust of the Milky Way. We see an overabundance of certain crystalline silicates like forsterite, which have a very specific, ordered atomic arrangement. In our galaxy, such pristine crystals are usually destroyed over time by cosmic rays and shockwaves, ground down into more amorphous, glassy grains. Their survival here suggests a different, more violent history. How could an entire galaxy end up with the wrong kind of dust? The answer lies in the forge of its collision. The immense shock waves from the galactic merger did not just trigger star formation, they also acted as a colossal industrial furnace for dust production. The violent compression of gas clouds and the furious outflows from supernova created unique conditions of temperature and pressure, conditions that favored the formation of these specific hardy crystals. It is as if the entire galaxy experienced a sudden, universe-wide tempering process, creating a breed of super dust capable of surviving the harsh environment. This anomalous dust is not a mere curiosity, it has profound consequences. Dust grains are the building blocks of planets, the seeds around which ice and rock coalesce to form new worlds. If the fundamental ingredients are different, what kind of planets might form from this exotic material? Could their surfaces be composed of minerals we have never seen, their geology and chemistry following rules written in a different cosmic language? The silent, microscopic grains drifting through the tadpole carry the blueprint for entire, unknown worlds. A patient time bomb ticks within the tadpole's disk, a stellar partnership with a violent, predictable rhythm. This is a recurrent nova system, a pair of stars locked in a cycle of theft and detonation that plays out over and over again. One star is a white dwarf, the Earth-sized core of a star that has already died, a diamond made of degenerate matter with the mass of a sun crushed into a tiny, dense sphere. Its partner is a normal, sun-like star, bloated and aging. They orbit each other so closely that the white dwarf's immense gravity acts as a cosmic siphon, relentlessly pulling hydrogen-rich gas from the atmosphere of its companion. This stolen material does not fall gently onto the white dwarf's surface. Instead, it accumulates in a searingly hot, dense layer on its surface, a volatile ocean of fuel under unimaginable pressure. For decades, this layer builds, waiting. Then, without warning, a critical threshold is crossed. The pressure and temperature at the base of this hydrogen ocean become so extreme that a runaway thermonuclear fusion reaction ignites. The entire surface of the white dwarf detonates in a colossal flash. In a matter of hours, the system's brightness increases by a factor of 10,000, outshining all but the most brilliant stars in the galaxy. It is not a supernova that destroys the star, but a surface explosion, a stellar flare-up that briefly turns this binary pair into one of the brightest objects in the tadpole. For a few days, it blazes with the fury of a cosmic beacon before slowly, over weeks and months, fading back to its normal, quiet state. The white dwarf, however, survives the blast relatively unscathed. The siphon soon starts again. The companion star continues to bleed its atmosphere, and the layer of hydrogen begins to build once more, resetting the clock for the next explosion in a few more decades. This endless cycle of accumulation and detonation makes this system a cosmic laboratory, a place where we can study the physics of thermonuclear explosions with a predictable timetable. But it also raises a profound question about its ultimate fate. With each cycle, the white dwarf may be growing ever so slightly more massive. Could this repeated feeding eventually push it over its own stability limit, triggering a final, far more violent explosion that would consume both stars entirely? This patient ticking clock may be counting down to a far greater cosmic event. A silent, high-speed river of gas is crashing into the Tadpole Galaxy. This high-velocity cloud is a colossal structure of pure hydrogen, streaking through the galactic halo and destined to collide with the main disk. Its movement is radically different from the rest of the galaxy, a clear sign it is an outsider, an immigrant falling in from the cosmic void. But where did this river of raw material come from? It could be a leftover strand of the primordial cosmic web, a filament of gas that has remained free floating since the dawn of time, only now succumbing to the tadpole's gravitational pull. Or it might be the ghost of a long-vanished dwarf galaxy, completely torn apart by tidal forces, with this cloud being the last visible remnant of its gaseous body, a galactic shroud falling back to its destroyer. As this cloud plows into the tadpole's outer disk, the consequences are both destructive and creative. The initial impact is a slow-motion collision of unimaginable scale, a gentle but persistent ram pressure that compresses the existing gas in the galactic plane. This compression can trigger shock waves that ripple through the interstellar medium, nudging stable clouds over the edge into gravitational collapse and sparking the birth of new star clusters. It is a gentle rain of creation, a cosmic fertilization event that delivers fresh fuel for future generations of stars. Yet this infusion is not entirely peaceful. The cloud's unique trajectory and composition can stir up the galactic disk, injecting turbulence and altering the magnetic fields. It is a reminder that galaxies are not closed systems. They are open to the cosmos, constantly accreting new material from the vast emptiness between them. This incoming river of hydrogen is a direct link to the tadpole's future, a delivery of the fundamental ingredient for stars, planets, and perhaps even life itself. How many other such silent, high-speed deliveries are currently falling toward unsuspecting galaxies, their arrival destined to quietly reshape the cosmic landscape? A jagged scar of glowing gas hangs in the void, the ghost of an explosion that refused to follow the rules. This is the remnant of an asymmetric supernova, a stellar death that tore itself apart in a profoundly lopsided manner. Its form is not a serene, expanding sphere, but a twisted, chaotic cloud with tendrils of ejected matter stretching far further in one direction than the others. The elements forged in its final cataclysm are not evenly distributed, but flung out in great, uneven clumps, as if the star itself was vomiting its insides into space. This chaotic debris field directly challenges our most fundamental models of how massive stars end their lives. For decades, the standard core collapse supernova model envisioned a relatively symmetrical implosion followed by a rebounding shockwave that blows the star apart in all directions. The asymmetric remnant tells a story of violent instability from the very first moment. The key likely lies deep within the star's final seconds. As the iron core collapses, the physics at the heart of the explosion may be inherently unbalanced. Neutrinos, those ghostly particles that carry away 99% of the star's energy, might not stream out evenly. A slight preference in one direction could create a neutrino rocket effect, literally pushing the exploding stellar material in the opposite direction. Another possibility involves the star's furious rotation. If the core was spinning rapidly as it died, the resulting explosion could have been channeled and focused out along the star's rotational axis like a fire hose of stellar debris. The most dramatic scenario involves the star's own magnetic field, wound up to unimaginable intensities during the collapse. This could have focused the entire energy of the supernova into two opposing, relativistic jets, with one jet being far more powerful than the other, punching through the star and carrying the bulk of the heavy elements with it. This lopsided death has profound implications. The uneven distribution of elements means that the surrounding space will be seeded with the building blocks for future planets in a very patchy, unpredictable way. Some regions will be enriched with iron, gold, and uranium, while adjacent areas might remain relatively pristine. It forces us to ask if our own solar system's specific mix of elements was the result of a perfectly symmetrical supernova, or if we too are the children of a chaotic, off-kilter stellar death. How many other stars die not with a uniform bang, but with a cosmic stutter, their final moments a turbulent, directional burst that forever skews the chemistry of their corner of the universe? Gravity itself has painted a ghost in the depths of the tadpole's tidal stream. Astronomers have mapped a region of space where the light from distant background galaxies is subtly, yet unmistakably, warped and stretched. This gravitational lensing effect reveals the presence of a massive object, a clump of invisible matter exerting a powerful pull on the fabric of space-time. Yet when they point every telescope they have at this spot, they find almost nothing there. No brilliant swirl of stars, no glowing clouds of gas, just a profound and puzzling emptiness. This is the dark galaxy candidate, a gravitational phantom that may be a galaxy made almost entirely of dark matter. It possesses the mass of a small dwarf galaxy, enough to hold millions of stars, but it appears to have failed at the very purpose of a galaxy, the creation of suns. The leading theory is that this object is a pristine pocket of the cosmic web, a knot of dark matter that formed in the early universe but never managed to pull in enough ordinary gas to trigger significant star formation. It could be that the gas was stripped away during the tadpole's violent collision, or perhaps it was blown out by the radiation from the first generation of stars in the universe, leaving this dark matter skeleton bare and isolated. Another possibility is even more profound, that this candidate represents a fundamentally different class of cosmic object, one where the ratio of dark to normal matter is skewed to an unimaginable extreme. In a typical galaxy, dark matter outweighs visible matter by about 5-to-1, a dominant but not total control. Here, that ratio could be 100-to-1 or even 1,000-to-1, a realm where the invisible substance is not just the anchor but virtually the entire island. If this candidate is confirmed, it forces us to reconsider what a galaxy even is. Is it defined by its stars or by its gravity? Could the cosmos be teeming with these dark ghosts, massive structures that float unseen between the brilliant spirals and ellipticals, their presence felt only when they bend the light of more successful galaxies behind them? This solitary, dark clump challenges the very narrative of cosmic structure, suggesting that for every galaxy we see shining, there may be countless others hiding in plain sight, their immense mass casting no light at all. A delicate, glowing hourglass hangs in the depths of the tadpole, its intricate structure a testament to a hidden dance. This planetary nebula, a final shroud of luminous gas, was sculpted not by a single dying star but by two. Its central star is a tight binary system, two suns locked in a close, fast orbit that dictated the nebula's every beautiful curve. As the primary star reached the end of its life and began to shed its outer layers, its companion was not a passive observer. Their rapid orbital motion created a complex gravitational field that acted like a cosmic potter's wheel, spinning the ejected gas into an elaborate shape far beyond a simple sphere. The outflows were channeled, sculpted by the star's dance into the symmetrical lobes, delicate rings, and fine radial filaments we see today. This is the ghost of a stellar relationship frozen in time. The entire structure is a fossil record of their orbital period, their masses, and even their orientation. By studying the nebula's precise morphology, astronomers can effectively rewind the clock and deduce the dynamics of the central system without directly seeing it. The two stars continue their waltz at the heart of this magnificent glow, now revealed as the true architects of this celestial artwork. What other stunning nebulae are actually the signatures of hidden stellar partners, their beautiful forms telling a story of gravitational collaboration in the face of certain death? A frantic blaze of creation scars the tadpole's spiral arm, a stellar nursery gone utterly berserk. This is the starburst region, a zone where star formation has been cranked up to a violent, unsustainable extreme. It is not the gentle, sporadic birth of suns seen in a calm galaxy, but a frenzied, all-at-once ignition, as if the very concept of a star factory has suffered a catastrophic meltdown. The trigger for this fury is written in the galaxy's twisted history. When the smaller galaxy tore through the tadpole, it sent immense gravitational shockwaves rippling through its gas-rich disk. These waves acted like cosmic bulldozers, violently compressing vast reservoirs of hydrogen gas that had been drifting peacefully for eons. Imagine a hand forcefully squeezing a dozen sponges saturated with gasoline simultaneously, each one bursting into flame from the pressure. That is the scale of the ignition here, where entire giant molecular clouds were pushed over the edge of stability in a single, tumultuous event. The consequences are both spectacular and self-destructive. The region is now packed with millions of newborn stars, a significant fraction of which are the most massive and volatile types. These stellar titans burn with a fierce blue-white intensity, flooding their surroundings with ultraviolet radiation so powerful it boils away the very gas clouds that gave them birth, effectively sterilizing the region and preventing future star formation for eons. Their stellar winds, screaming outward at millions of kilometers per hour, carve immense cavities and create turbulent shock fronts that rip apart smaller, fledgling protostellar disks before they can even properly form. This starburst is a spectacular but short-lived fireworks display. The largest of these stars will live for only a few million years before exploding as supernova, their sequential detonations adding more violence to the chaos and seeding the area with heavy elements. This cycle of frantic birth and sudden death creates a feedback loop of incredible power, a self-regulating and self-limiting explosion of cosmic activity. The starburst will eventually consume its entire fuel supply and burn itself out, leaving behind a glittering but aging cluster of stars and a hollowed-out gaseous void. What does such a furious, unsustainable burst of creation ultimately leave behind? And is this the violent adolescence that every great galaxy must eventually pass through? A sharp, luminous edge cuts across the tadpole's tail like a celestial cliff face. This is the tidal shock front, a boundary of cosmic violence where the galaxy's own debris is crashing into itself. The long tail is not flowing smoothly. Different sections of this river of gas and dust are moving at different speeds, pulled by the complex gravity of the distant core and the lingering effects of the ancient collision. This shock front marks the precise line where a faster-moving inner stream of material is plowing directly into a slower, more sluggish outer region. The collision is a slow-motion train wreck on an astronomical scale. As these colossal clouds of hydrogen gas slam together, they are not gently merging, they are compressing with immense force. The gas at the boundary is squeezed to incredible densities, its molecules driven together so violently that the pressure and temperature skyrocket. This creates a searingly bright ridge of emission, a wall of superheated plasma that glows fiercely across multiple wavelengths from visible light to radio waves. This compressed wall is far more than just a pretty light show. It is a stellar production line. The intense pressure is the universal trigger for star birth, forcing the giant clouds of gas to collapse under their own weight. All along this luminous ridge, new stars are igniting in a synchronized wave, a linear firestorm of creation tracing the path of the collision. It is a perfect demonstration of chaos giving birth to order, a runaway chain reaction of star formation set in motion by the simple, brutal physics of a cosmic traffic jam. What other invisible boundaries are silently shaping the destiny of galaxies, their sharp edges marking the frontiers of new stellar empires? A single, brilliant pinprick of heat glows in the darkness, a mystery written in pure infrared light. This object, known only as an unidentified infrared source, is a cosmic paradox, blazing with thermal energy yet revealing almost nothing to our optical telescopes. It appears as a perfect point, suggesting a single, compact object, but its infrared signature is so powerful and unique that it defies comparison to any known catalog of stars, nebulae, or galaxies. It is a true astronomical enigma, a nameless entity whose very nature is hidden behind a shroud of its own warmth. The central question is simple yet profound. What could possibly produce such intense heat while remaining so visually dim? The possibilities stretch our understanding of cosmic phenomena. It could be a stellar nursery of unprecedented density, a cocoon of gas and dust so thick that the brilliant young stars blazing within are completely smothered, their fierce light absorbed by the surrounding material and re-radiated outward as this diffuse warm glow. In this scenario, we are seeing the thermal echo of a stellar birth too well insulated to witness directly. Another, more exotic theory points to a dying star in its very final act. This could be a pre-planetary nebula in a fleeting, critical phase, where the central star has not yet grown hot enough to ionize its ejected shell of gas. The entire system would be a warm, expanding cloud, visible only in the infrared, a brief cosmic sigh before it blossoms into a brilliant, visible nebula. Or the source could be something far more alien, like a rogue planet, a colossal gas giant untethered from any star, drifting through the tadpole's depths. After eons of cooling, its internal heat would still leak out, creating a faint infrared signature just like this one, a dark, wandering world betrayed only by its own residual warmth. The most tantalizing possibility involves an active galactic nucleus from a galaxy so distant and so heavily obscured by dust that its brilliant core is completely invisible, with only the faint, redshifted heat from its dusty torus managing to reach our instruments. This single point of heat is a powerful reminder of the limits of our perception. The universe is not only stranger than we imagine, it is often invisible to our most familiar senses, communicating in wavelengths of light we must learn to translate. What other fundamental pieces of the cosmic puzzle are hiding in plain sight, waiting for us to look with the right kind of eyes? A ghostly thread of pure heat weaves through the tadpole's halo, a filament of gas so scorching it only reveals itself in the high-energy glare of X-rays. This is the coronal gas filament, a river of plasma heated to millions of degrees, tracing invisible lines of force that structure the entire galaxy. Unlike the cold, dark clouds where stars are born, this filament is composed of matter in its most energetic state, where atoms have been stripped of their electrons, creating a superheated, electrically charged soup. It glows not with starlight, but with the furious emission of atomic collisions, a searing signature written in a language of pure energy. How does such a delicate structure survive in the harsh emptiness of the galactic halo? Its very existence points to a hidden scaffolding. The filament is likely stretched along the galaxy's powerful magnetic field lines, its ionized particles trapped and guided by these invisible threads like iron filings aligning around a magnet. This cosmic cage prevents the unimaginably hot gas from instantly dissipating into the void, confining it into a long, coherent strand. Another possibility is that this thread is the lingering shock front from an ancient titanic supernova. The blast wave from a stellar explosion, traveling for millions of years, could have swept up and heated this gas, sculpting it into a linear structure as it expanded. The filament is a fossilized echo of that long-forgotten detonation, its heat a remnant of the violence that created it. This delicate, burning thread is more than a celestial curiosity. It is a key part of the galaxy's circulatory system. Theorists suggest these coronal filaments act as conduits, funneling superheated gas and heavy elements from the star-forming disk out into the galactic halo, where it may eventually cool and fall back in, fueling future rounds of star birth. It is a single thread in a vast, unseen web of energy and matter, a reminder that a galaxy's true structure extends far beyond its visible stars into a realm of seething, invisible forces. What other hidden pathways are channeling the galaxy's lifeblood through the darkness, their presence revealed only by the faint, hot breath of X-ray light? Deep within the tadpole's sprawling halo, a silent relic drifts, a bubble of time preserved for over 13 billion years. This is the primordial gas pocket, an isolated cloud of hydrogen and helium that has miraculously escaped the cosmic pollution of stellar evolution. Its composition is stunningly simple, a near-perfect reflection of the universe's chemical state just a few 100 million years after the Big Bang. before the first stars had forged the heavier elements that would seed future generations. This pocket is the universe's most pristine library, its pages written in the simplest atomic alphabet. Finding such a pure sample is like discovering a sealed vial of ancient atmosphere from a time before life began on Earth. The gas should not have survived in this state. For billions of years, shockwaves from supernova and the fierce stellar winds from countless suns have churned the interstellar medium, enriching it with carbon, oxygen, iron, and all the other elements we consider the building blocks of planets and life. This cloud, however, was left behind, a forgotten backwater in the cosmic flow. It likely formed in a vast, quiet void, a region where the gravitational pull was too weak to trigger the collapse and ignition of the first stars. It remained a sleeping bystander as the cosmos evolved around it, a pocket of potential that never realized its purpose. Its survival within the chaotic Tadpole Galaxy is the ultimate paradox. The same violent collision that twisted the galaxy and forged so many strange objects must have somehow sheltered this fragile bubble, perhaps by flinging it far out into the calm halo where it could continue its ancient slumber undisturbed. Studying its light is like listening to a pure, single note from the universe's infancy, a tone unpolluted by the complex symphony of stellar death and rebirth that followed. This gas is the raw material from which the very first mythical population 3 stars were born, giants of pure hydrogen and helium that have long since vanished. By analyzing this pocket, we are not just looking at a cloud, we are staring back at the blank canvas of the cosmos, seeing the fundamental ingredients before the first brushstroke of starlight ever touched them. What other untouched relics are hiding in the dark corners of other galaxies, holding the unspoiled recipe for existence itself? From warped black holes to runaway stars and dark matter ghosts, our journey through 50 of the Tadpole's strangest inhabitants reveals a cosmos of breathtaking diversity. This single, distorted galaxy is not merely a collection of oddities, but a unique cosmic laboratory where the fundamental laws of physics are stretched to their limits. Each object, from the lopsided supernova remnant to the primordial gas pocket, tells a chapter in the same epic story of chaos and creation. The tadpole's violent birth and its ongoing turmoil have created conditions impossible to replicate elsewhere, offering a front-row seat to processes that shape the entire universe. It challenges our most basic assumptions about how galaxies live, grow, and interact, forcing us to reconsider the very nature of matter, energy, and the invisible forces that bind the cosmos together. This galactic tadpole, in its beautiful imperfection, shows us that the universe's greatest mysteries are not just about the darkness we cannot see, but about the brilliant, chaotic, and utterly strange light we can. What other cosmic laboratories are waiting in the depths of space, ready to rewrite the rules we thought we understood? We have journeyed past 50 of the universe's strangest creations, all housed within one spectacularly distorted galaxy. Now the story continues with you. Which of these cosmic inhabitants captivated you the most? Was it the silent, drifting phantom of a dark galaxy, or the frantic, brilliant rhythm of the X-ray binary's heartbeat? Share your choice in the comments below, and let's continue this conversation across the cosmos. For more deep dives into the universe's greatest mysteries, be sure to subscribe. The Tadpole Galaxy is just one of countless cosmic laboratories, each one a testament to the boundless creativity of the universe. As you look up at the night sky, remember that every pinprick of light holds a story of chaos, creation, and endless wonder, all waiting for a curious mind to discover.